Hi there, guys. So this is 8F from the book, and so far you've done 2 exercises on complex numbers. You've done a lot of conceptual work, a lot of thinking about how complex numbers can be represented, and 2 different forms. We've got a polar form and we've got the Cartesian or rectangular form. And now in the third of the exercises, without you having much practice with the actual arithmetic behind complex numbers, we're now chucking in a third version of how you can write complex numbers, which seems complicated, but actually it's making life a little bit easier. Now, this comes from, skip me there. So this is what we're talking about here. We're saying, look, we've got r cis theta, that's our polar form, which we're dealing with, where r is the modulus, or the absolute value of the vector. In other words, the length of the vector, I keep saying that, a complex number, the length of the complex number there, and theta is the argument of the complex number. Okay, so that's what we're used to from the previous exercise. Here's another way of writing down a complex number, and now here's the final way of writing down the complex number. So we're saying, in fact, you can do r cis theta, which is this. Okay, same thing, can now be written, as well as it having this Cartesian format, you can now write this as r e to the I theta. Okay, now this is known as Euler's form here, and essentially this is also Euler's formula if we get rid of the r in front of both. But this is Euler's form. So we have a polar form here, we have an exponential form, or Euler's form here. So again, they can also call it exponential form. Now, this also shows you a modulus argument form here, because we still have the modulus and we still have the argument up here. So it's still giving you the same, what they call parameters here, parameters being r or theta there. Okay, so I've actually proved this towards the end. I've just done a video for that. I'm going to attach that to the end of this. So if you're interested in the proof, then by all means look at that, but that will be beyond this course. So all we need to do is know that we can write things like this in this format here. Okay, so that's actually really nice, because if this is z, and again, z could be written like this as well. That's the third form there. So if we wanted to do z to the power of n, that's the same as this to the power of n. And this to the power of n would be r to the n e to the I n theta. Okay, that's just me saying this whole thing to the n, and you know, like when we have a b to the n, you can bring the n onto both of those factors in the product. Okay, so that's what's happened here, and this can now be written as r n. And this, of course, can be written in this format if we replace theta by n theta, because there's n theta there now. So this is now r to the n cis n theta. Okay, and that's a really nice result. And in fact, that's called de Moivre's formula. And essentially, here we're saying cis theta, they're saying cis x to the power of n. That's what we're coming up with here at the top. So that's cis theta, or cis x to the power of n, is equal to cis nx. Right, that's pretty powerful stuff, in fact, because that's saying that this is the same as r cis theta to the power of n. Okay, or in other words, r to the n theta, which is the same thing. Yeah. Okay, so now you might think that's not particularly interesting just at the moment, but it's interesting in terms of multiplying complex numbers together and seeing where they end up on the Argand diagram. So let's have a quick look at this one. So let me just take a little bit off there so I can write further here. So we're now saying that z to the n is essentially r to the n cis n theta. Okay, so if we come up with, let's say we've got here, I don't know, 2 here. Okay, this is the length. That's going to be the r in this case, and this is our theta. This is our complex number. So this would be z. This is a 2 here, by the way, and this is z. Okay, and so if we're going to times z by itself, so z squared would end up with twice the argument. Okay, so twice the argument would perhaps be around to here, and we'd get 2 squared coming out of here because the length of this thing was 2, so 2 squared being 4. So there we go. This would now take us up here. So we've now got z squared having a length of 4 and an angle of 2 theta. Okay, and if you did z cubed in this case, that would now go around 3 theta, and that would have a length of 8. That would have a length of 8 here because that would be 2 cubed. So that would be somewhere up here. And again, let's see if I can put 4 theta in. If I go around 4 theta, and this would have a length of 16. So you can see the implication here when we're moving around the Argand diagram, of doing powers of complex numbers. Now, this is useful for transformations, in fact. So we can transform points really quickly by applying, by turning coordinate points in your normal coordinate system into complex numbers and then dealing with the algebra of complex numbers. So that's the importance of this. Okay, now if you just had instead to put a complex number, let's just say this is a length of 1, there's theta. If I say that that's my original z here, then the next complex number is going to be 2 theta around, and 1 times 1 is still going to have a length of 1 there. Okay, so that would be 2 theta, and then of course we do that again. We're going to have 3 theta as our term there, and this would still have a length of 1, and this would be z cubed. So you can see essentially that when you've just got a length of 1, and when you multiply complex numbers together, they just move around in a circle, in the unit circle, in fact, in this case, where we have a radius of 1. Okay, so they'll be somewhere on that circle here. Okay, so let's have a look at a question here. And let's take one of these from the book. So now I'm going to skip the investigation, although obviously the investigations are nice if you have time. We'll go and have a look at those. And we're going to, here they talk about the powers of complex numbers, which we've just dealt with. And we're going to look at example 9, and there's another investigation that comes after that. Let's look at example 9. Okay, so obviously you can use the calculator in this one, and there's a calculator link that shows you how to do this on your calculator too. But anyway, this one says given tan of theta pi divided by 6. So remember, pi is 180 degrees. So it's talking about tan of 30 degrees. And there's one of our ratios for special values of theta. And we can get that out, by the way, from this triangle here. If we take the equilateral triangle 2, 2, 2, that's the length of 1 at the bottom there. For half of the triangle, there's a right angle triangle. This is the square root of 3 if you apply Pythagoras in this right angle triangle. And pi over 6 is here. That's our 30 degrees because we split the 60 degrees at the top. And you can see that opposite over adjacent in this case is 1 over the square root of 3. So this is not difficult to find, but 1 over the square root of 3 you also know as square root of 3 over 3 if we rationalize the denominator by timesing top and bottom by square root of 3 over square root of 3. Okay, so that's just where that comes from. So find the modulus and the argument of this thing here. Okay, so this is just information that they've given us. Maybe that's going to be useful. But the question is, find the argument of this. Now I'm going to come up with a little diagram for this. So there's the real axis here and the imaginary axis. So this is minus root 3 back here. So that's somewhere between -1 and -2. And we've got minus I here as well. So maybe -1 there on the imaginary axis. You don't need to put the I as well, because it's already implied by being imaginary. So we're going to put this point here, join it up to the center. This is our Z. And now we need to find the modulus and the argument. The modulus of this is simply going to be using Pythagoras. So that's saying minus root 3 squared plus -1 squared, all square rooted. So that's the modulus of Z, or the size of Z. That's also equal to R, of course. And so that's giving us square root of 4, which is equal to 2. So R is equal to 2. And the argument of this is going to be this angle here, or potentially negative this angle here. Okay, so given that we know tan of pi over 6 is 1 over the square root of 3, so 1, if we draw this triangle out like this, we've got a length of 1 here, a length of the square root of 3 here. So this is going to be pi over 6, okay, opposite over adjacent there. So it must be this angle here being pi over 6. So this is pi over 6, and we need to add that on top of pi. So pi is 180 degrees. So let's take that back a little bit. Okay, so this is pi over 6. This is pi. And so now we can see that we have 6/6 of pi plus 1/6 of pi. That gives us an argument. So theta there is equal to pi plus pi over 6, which is 7 pi over 6. Now, I note that in the book, they actually give it as the backwards angle from here. Okay, so they say, well, that's the same as minus 5 pi over 6. Okay, so we can either go forwards, but we can also measure the angles in a negative sense as well. So in this direction, we would be going back 5 pi over 6. Okay, but both answers are fine there, so this is fine. I'll keep with the positive value. Okay, and then in part B it says, find an expression for z to the n, and hence the smallest value of n for which the imaginary part of z to the n is 0. So z to the n is let's put this in format which is nicer to work with powers. Where it's nicer to work with powers, so we'll say z to the n equals, now we know that r is equal to 2, so we've got 2 e to the I, and we've got here 7 pi over 6, so we've got 7 pi over 6 there. Okay, and we want to raise this to the power of n. So this is essentially our complex number. We've just written it in Euler's form there. And now we can say we've got 2 to the n e I 7, hang on, that's right, n 7 pi over 6. I've just brought the n on the inside there. Okay, now it says find the smallest value for n for which the imaginary part of this complex number is equal to 0. So we've used the Euler's form here to work with the powers, which has been good. Now, what's the imaginary part of this? Well, I think I'm going to need to flick this back into the polar format here. So this is going to be 2 to the n, and I'm going to write, so I've got cis theta here, so that's cos of n 7 pi over 6 plus I sine of n 7 pi over 6, close brackets. Okay, now we want to know when is the imaginary part of this equal to 0. So this is the imaginary part. We want to know when is this equal to 0. So running out of space a little bit. I'm just going to rub out this top stuff and put it in there. Okay, so just going up here. When is the imaginary part equal to 0? So imaginary part of z to the n equals to 0 means that we've got 2n sine n, let's write that meter, sine n 7 pi over 6 has got to be equal to 0. I don't need to put the I there. Now I can now divide by 2 to the n. I didn't really need that as well. And then we're thinking, what's the value of n? So what's it saying? The smallest value for n, for which this value, that gives z to the n, sorry, which makes the imaginary part equal to 0. Now the smallest value of n is going to be 0. But I suppose z to the 0 is a pretty boring example of making this work. So n has got to be equal to 0. If you put 0 in, then you get sine of 0 is equal to 0. Okay, so I think it really needs to say n is a positive value here. So we're saying that we're looking for the next one. So let's look at the sine graph here. Okay, so sine is equal to 0, 0 at pi and at 2 pi. So this thing here inside, for us to hit the next 0 essentially, to give us sine of something, sine of pi is equal to 0, we're going to need to set this equal to 0 here. So sorry, equal to pi. So that would imply that n7 pi over 6 equals pi. The pi can cancel. It's obviously leaving us with a 1 here. So we can take times by 6 and divide by 7. So n is going to equal to 6 divided by 7. Okay, so at this point I checked the book and realized that the book wasn't allowing this solution here. In fact, the book wanted n to be a natural number. So I think perhaps that's implied through this question. So we wouldn't be taking necessarily powers of z, which is, say, for example, to the power of 1.5, so rational powers here. But I think if this was an exam question, it would definitely say that n belongs to your natural numbers. So this isn't a natural number here, so this one wouldn't be allowed. So the question is, how do I then find the value of n, the smallest value of n, which is going to work? Well, so let me just take this back a little bit here. And we're thinking here, if n has to be a natural number, well, again, you can still cancel the 1 and the 1 there. Okay. Well, that would give you an exact solution, in fact. So that's giving you this solution here. That's giving you n is 6 over 7 for this particular solution, but that's actually not good enough. So actually, we need another solution, another amount of pi. So we can see that this is hitting on 0, 1 pi, 2 pi, 3 pi, 4 pi, so on, and so on. And so we could say that this is actually equals to k pi. Okay, that's perhaps complicating things a little bit, because you can perhaps just see that in order to get rid of the sixth, you're going to need to put in n is equal to 6. So n is 6 is the first value, which gives you 7 pi. So that gives us a k, which is then, again, a natural number itself. Okay, so this would imply, under the condition that n has to be a natural number, that n has to be equal to 6. Now, obviously, if n is 12, that would also cancel with the 6, leaving us with 2 there, but that wouldn't be the smallest value. Now, this likewise works when you're dealing with minus 5 pi over 6 as well, like the book version. Because again, when you times by 1, 2, 3, 4, 5, you're going to get some fraction in terms of sixths. But when we times by 6, the 6 is going to cancel, so giving us an amount of pi, so a natural number times by pi there. Okay, so n is 6 is the one which is working, which is the natural number which is working there. Now, I'll look back at the book in a second. There's a little mistake in the book, actually, so I'll show you that too. And the book has not done this. I've done this to make some sense of things, but the book has not. Okay, so n is 6 is the answer, but we still haven't answered the question because it says, and for this value of n, give z to the n in Cartesian form. Okay, so now we've got to change back this, so z to the n, so z to the 6, we need to come up with this here. We need to put that back into Cartesian form there. Now, again, that's fairly straightforward. So 2 to the power of 6 is 6 to the 64. So z to the 6 would give us 64. Let's just do a little working out on the side here. And then times by e, the 6 is going to cancel with 6 here. And that's going to give us I 7 pi. Now, again, that's going to be really easy to change back into this form. But, you know, you can see that we could draw that one out if we wanted to. Let's actually do that to see what it looks like in terms of Cartesian form. So let's get rid of this here. Okay, so, and then let's come up with this. So we've got here 64, so the scale is going to need to be big on these axes here. So real axis and imaginary axis. And we've got 7 pi. So 2 pi takes us around here. Another 2 pi takes us to 4 pi. 6 pi ends up at the start as well. And pi, another pi takes us around to here. We're going in this direction. We're going to be 64 in this direction, in fact. So we're going to be minus 64 here. So this is where z to the 6 is. And actually, that one's quite easy to draw because we can see that this essentially takes us to 180 degrees or pi radians around from the positive real axis here. Okay, so in terms of the Cartesian form, we can just say we've got minus 64 plus no lots of I. In other words, just minus 64. Okay, let's check out what they're doing in the book. So let's see, so they're getting minus 64 as the answer there. Let's just take this version, which they've got for part B. And they've done it slightly differently, but there's also a mistake here in that they've put the NI there. So whichever student they've given to type this up has probably not understood complex numbers themselves. Definitely give it to a postgraduate student, eh? So this should go up here. Okay, so this really should be z to the n equals 2 to the n e to the, and they've used minus 5 pi over 6 n I there. So perhaps a bit neater than how I wrote it. Okay, I used, of course, 7 pi over 6 instead of this one here. Okay, now, again, they've done the same kind of idea as what I did. And again, they've come up with the k pi because we know that this has to be, this number here essentially has to be a natural number. So that's the same as what I've done from that point onwards, but that's just the mistake that there is in the book there identified. Hopefully that will get ironed out when people email into Oxford. And so perhaps in a few months' time, this will be fine in the book as well. This is the online version of the book, which I'm using here. Okay, guys, so after that, we've got movement in the Argand plane, which is what I've already talked about. So I'm not going to talk about that again. So that's about this sort of movement around in a circle. So I'm not going to talk about that again. Here's 8F. Again, there's not many questions there. We've only got 6 questions. So again, I suggest you get maximum practice with this one. Here we go. There's a bit here which says this formula is widely regarded as the most beautiful in mathematics as it combines the 5 fundamental numerical constants into a simple formula. They're talking there about Euler's formula, moving to obtain Euler's identity being e to the I pi plus 1 equals 0. So you can show Euler's identity there. And when they're talking about the 5 fundamental numerical constants. They, of course, mean e, pi, I, 1, and 0. Okay, right, good stuff. Hope you're enjoying this. The proof of Euler's formula is coming up now. Hi there, guys. So I'm going to prove Euler's formula in this video here, and we're basically talking about our complex numbers written either in Euler's form, so we would have r e to the I theta, or also r cis theta, which would be our polar form there. And so these two things are equivalent. This cis theta here is essentially this thing here, and r is, of course, on the Argand diagram, it's the length of your complex number. So there's r, and theta is the argument of your complex number. It's measured from anti-clockwise from the real axis on the Argand diagram. Okay, there's z in this case. So this is just equal to z here. And what we're going to try and prove is just this part. So we don't need the r and the r there. Obviously, if we times both sides by r, then you obviously get the same, you get the result that we need. Okay, so a lot of books skip over this. That's why I'm giving this proof separately here. And also, I've just taken this one from a choice of proofs here. And so there's proofs from, if you put in here, let's go, what is this? This one is called Euler's formula. And if we have a look at the proofs here, I've chosen the second of the proofs here. So I'm just really working through the second proof here. Okay, so here we go. So little proof, let's just find this thing here, say that what we're doing. And we're going to say, to start off with, let e to the I x rather than e to the I theta equal to r cos theta plus I sine theta. I'm going to put that in brackets. It's already factorized out my r there, and this is, if you like, your cis theta. Same thing. Okay, so deliberately I haven't put an r on the front here. So I'm going to show what r is equal to in this situation. Hopefully r is going to be equal to 1. And I'm also going to, I've not got theta here, which you can see here as well. And again, hopefully I'm going to prove that x is equal to theta in this question. Okay, so the way in which we're going to do this is differentiate both sides with respect to x. So if I differentiate this side with respect to x, that's just using your exponential laws with differentiation. So using the chain rule essentially, and obviously e to the x, differentiating to be e to the x. If you've got a constant in front of here, then the chain rule says that we need to put a constant in front there as well, times by the derivative of u, if you like, our function inside the function. Okay, so this one is going to give us I e to the I x under differentiation. And just to show what we're doing on the other side, we're saying d dx of this thing on the right-hand side, which is r. And then let's just type in cis theta for brevity there. So we've got essentially two functions inside here. We have r, which is potentially dependent on x, and we've got cis theta, which is also potentially dependent on x. Now, presumably, some of this on this side is going to be dependent on x, because this is dependent on x, and that's how we set the whole thing up. So we're going to assume that this and this are two functions which are dependent on x, and we're going to differentiate with respect to x. Okay, so essentially what we're doing here is differentiating a uv. So we're going to use the product rule for differentiation here, and that becomes uv dash plus u dash v. Okay, now if you're not sure where this is coming from, then you need to go back to the product rule for differentiation, because that will have come earlier in whatever course you do. Okay, so now we're going to differentiate this thing here, and so we've got u is equal to r, and r is some function of x, so we could say r in terms of x here, but we don't know what that function is in terms of x, but we know that it must depend on x because there's x involved on this side. or if that doesn't depend on x, then the other one certainly does, and potentially that's a constant. And so then we've got v is equal to cis theta here. Okay, so when we differentiate this, we're going to get r, so that's this bit here, and then the derivative of this. Now the derivative of this, cis theta, is going to give us minus sine theta. We get minus sine theta there, and the derivative of this is going to give us plus I cos theta. Okay, and we've differentiated this with respect to x, so we really need here an extra d theta dx. So essentially what we've done is we've taken dv dx, and we split up dv and dx, and we put in this d theta d theta. So now we've differentiated with respect to theta. We didn't differentiate with respect to x. We've done this part, that's this part here, and now we need to do d theta dx. So we're just going to put that on the end. Okay, so that's essentially us applying the chain rule there. So we've got d theta dx written on the end. Now, obviously, that's only this part, so we need the other part as well. So we've got plus, and we need u dash. So that's just the derivative of this with respect to x. So that's just dr dx. That's the best we can do there. And then in brackets, we're going to have v, and v is just this thing here. So it's your cis theta, but I'll write it out fully. We've got cos theta plus I sine theta there. Okay, so essentially we've now differentiated both sides, and that's what we've got down to. Okay, so at this point we can now replace back in this thing here for e. Sorry, put that back. That's Rx there. So we've now got e to the ix is still this. That's how we defined it in the first place. And I can see that that is turning up here, but without the r. But in particular, it's turning up here. Okay, so I'm going to replace this on the left-hand side. So I'm going to put in here I, and then so it's I times by this. Actually, I can do it all at once. I can say that that's I r cos theta, and then it's going to be minus r sine theta there. Okay, so obviously when we times this by I times I is going to give us minus 1. That's where we're getting this minus from. So that's just us replacing this for this thing here. Okay, and then timesing by I, and I've already done the timesing by I. And now on the right-hand side here, these two things need to be the same. So we've got on the right-hand side again, well, the whole of this. So write it all out again. I think I won't write it all out again. And so then you can compare on both sides here your real parts. Okay, so the real parts here are going to be r sine theta minus r sine theta. And on the right-hand side here, so this bit here, we've got minus r sine theta d theta minus r sine theta d theta dx, and then we have as well from this part, the real part is going to be plus cos theta dr dx, and then by comparing the imaginary parts on both sides of this equation that's coming out here, then, and obviously the derivative needs to be the same on both sides, so we could potentially create that as a triple equals here, saying these are identities. And so in comparing the imaginary sides here, you've got r cos theta here, so that's the imaginary part of this complex number here, and that's just the coefficient of I. And then on the right hand side, we can see that we've got I r cos theta d theta dx, and we also have Sorry, we don't need the I. And then we also have sine theta dr dx there as well. Okay, so now we've compared both the real and imaginary parts of both sides. Now, you can see when you're looking at these sides, you can see the solution quite simply, and I'm not going to go into too much algebra here, but you can essentially see that we have this here. If only this is equal to 1. And if this is equal to 1, then this is going to have to be equal to 0 to make this equal to 0 here, to make this whole part equal to 0 for both sides to equate. So I'm just sort of doing some trial and error here, and I'm going to put that 0 in. I'm going to see if that works on the other line. You can see, in fact, it does work on the line underneath as well. So again, this is 1 here, and this is 0 here. And again, that's working. So definitely a solution here is d theta dx is equal to 1 and dr d theta is equal to 0. Okay, now I'm struggling for space on this one. So let's just put down here dr dx is equal to 0 and d theta dx is equal to 1. Now, if you integrate both sides there, you'll see that r is equal to some constant, essentially. So integrate both sides there. And if we integrate both sides of this, we'll see that theta is equal to theta plus some other constant. Let's call that C1 and C2. Okay, so actually it turned out that R wasn't dependent on X, it was just a constant. Okay, but theta here is now, made a little mistake there, haven't I? That's equal to X when I integrate both sides, plus C2. You can see that theta is now dependent on X. Glad I saw that one in time. Okay, now the initial starting condition from this, you can see that if we put in X is equal to 0 here, we're going to get out 1 here. So e to the power of 0, anything to the power of 0 is 1. Now, to get out 1 from this, we're going to need to eliminate this part here, so the imaginary part, and we just need to end up with this part here, r cos theta. Now, to eliminate this, we could set theta equal to 0, okay, and that will get rid of this. But if we set theta equal to 0 here, so there's now no imaginary part, and then this part is going to give us cos of 0 is equal to 1. That will give us 1. So theta is 0. This gives us 1. This gives us 1 here, and therefore r has got to be equal to 1 as well. Okay, so that's a starting condition. That's definitely a combination that needs to work, that when we have theta equal to 0 and when r is equal to 1, x is equal to 0. So that's definitely a combination that needs to work with our equations. So again, let's just go through that one here. If we put in 0 here, then this disappears because sine of 0 is equal to 0. Now we've got no imaginary parts. Cos of 0 now is equal to, let's change that up. Cos of 0 is now equal to 1. Now if I put 0 in for x as well here, that gives me an answer of 1 out here. So now I've got 1 is equal to 1 times by 1. And so when theta is 0, r is 1, and x is 1 as well. Sorry, x is 0, giving us 1 on the left-hand side. Perhaps it's clearer to say that when you say when x is equal to 0, theta being 0 and r being 1 is a combination which works. And that combination which works then has to also work in these formulas here. So now we can say, okay, well, r is equal to 1 gives us our constant. So now r is equal to 1. And also, theta being equal to 0, when x is equal to 0, means 0 equals to 0 there. This is 0 equals to 0, and then C2 is equal to 0 there. So in other words, theta has to be equal to x. Okay, so essentially we've now proved this thing here, because we've now said that x is equal to theta, that's coming from this, and we've said that r is equal to 1. So given this starting condition, we know that we have e to the I theta there, and we also have on the right hand side here r being equal to 1. Now it would be completely fine for us now to times both sides by r, and then we get to our normal polar form for complex numbers, or our Euler's form there for complex numbers as well. Either way, both of those forms give you certainly the r at the front when we factorize that thing out as well. But it also gives us the argument of the complex number there, this position here at the top as our index number there. And you can see that that's the argument in here as well. Okay, so we've shown that Euler's formula is working. We've proved this thing here. And now, instead of writing complex numbers like this, we are allowed to write complex numbers like this. All right, well, thanks for listening, guys. If you are interested, you can have a look at the other two proofs. So there's a proof using power series here. It says we're using Maclaurin series, I think. Or hang on, they're using the Taylor series there. Not sure which, but it's using power series there. And then there's another proof based on differential equations, but it doesn't give you the full working out of that one. Okay, so we've just gone through this one here. Thanks for listening, and well, good luck for the exercises if you're working on those exercises. Otherwise, hope to see you back for another video later on.